Okay, so it's not going to take too long, but two things. We will be sharing every step of what we have done in an annotated R script so you can replicate every step of the analysis that we'll be doing here. So don't get intimidated if you see some codes and they look scary, or if you are unable to write them in time. We'll be sharing not just this PowerPoint, but also an entirely curated uh, R script, annotated R script, where we will try to write down what each step in particular does. But to analyze occupancy data, as we started discussing earlier, you can use presence software, which is, I think, one of the most widely used software today. There are more than 1,000 publications which have used it already, and the number keeps growing. There are a few problems with presence. It requires a Windows based interface. So if you have Mac, then you have to get a window. What is it called, Justine? There's something you do to get on Windows and use it, or you have to use a remote desktop or something. But we will be using R, and the main reason is A, of course, because it's not then dependent on which operating system you have, but it also becomes much more reusable and replicable. So whatever steps you follow, you don't have to cram them, you don't have to remember them. Once you've run an analysis successfully, you can just reuse the same set of codes for your other analysis, improve them if you want to, tweak them, modify them if you want to. But the reusability and the speed with which new analysis can be done increases substantially. So that's one of the reasons why I will go through R. Also, to keep in mind that everything that we will be doing here, we hope you will be able to do it by yourself. And for you to be able to do it by yourself, it makes it a good idea to have a script that you can then make use of. So what is R? I think most of you might already know what is R, but it's a free programming tool that can be downloaded from this link above, cran.rproject.org, and it's today one of the most popular data analysis and programming languages and environments. And again, if you're well versed with R, super, you'll be able to move very quickly. Even if you're not, the beauty of R is you can just replicate the same work that anybody else is doing by going through those commands. We will anyway strongly recommend that you and encourage that you take some basic courses in R, and please do not get intimidated by the command lines. I know a lot of people personally as well who feel a little intimidated because of the command line structure as opposed to a graphical user-based structure. But you'll start seeing the value in it, and once you annotate your codes properly, these codes become, not only they make your life easy, save you a lot of time, they become your friends, and then you'll start seeing the value of using R. Just to give you one simple example, until last year, I would only use presence software. R presence I hadn't been introduced to. Last year in September, we saw it for the first time. And since then till now, we have at least 4 different manuscripts. 2 of them have already been published, 2 are in press. I think 1 is in review, 1 is in press. The speed at which we could turn around analysis has gone up exponentially. So I also see huge value in upgrading from presence software to R presence, just for the sheer speed at which you can do a lot of work, data manipulation of models, and further tweaking your work. So very highly recommend R. And we prefer to use R on an interface called R Studio. It's a workspace. Some of you again might already know it, but those of you who are seeing it for the first time can see how this R Studio workspace looks like. In the last slide, I showed you where to download it from. You just go to rstudio.com, get the free version. You don't need to get the paid version. There's not much we gain at this point in time. But again, if you're an expert, if you're a pro already using a paid version, I mean, you need to teach us how to use a little bit of it. So please feel free. Whatever work we will do today, everything can be done with the free versions of R Studio, and of course all the packages which are available for free. Now we use R Studio because it allows several conveniences, and saving your work is much easier. You don't have to go back to step one all the way to replicate some of your works. So it's much easier to repeat a lot of the analysis that you're doing. I'm sorry, I'm not seeing chats right now, but yep, there is yes, Chloe, there is a non-free version of R Studio. In fact, there are 3 versions of non-free versions of R Studio that you can look for. Yes, agree, Helena. You can, I mean, feel free. Whichever environment you're comfortable with, whichever workspace you're comfortable with, feel free to use that one. So the key thing to remember here is, again, for those who don't use R already, in R Studio, we enter the data in, we enter our commands in this source panel where you type your codes. The codes are not run until you use Control plus Enter or press this run button that you can see. Where is it? Where did the run go? This one. This run button. Till you don't press the run button, the code doesn't run. You can use it almost like an editor window, type whatever you want. The moment you press Control Enter, that's when the command is executed. The other one, the command, I think this one is called the environment and history panel, where you can review the objects that are in your workspace. You can review tables, you can review other files that you have, objects that you have created, and you can kind of import stuff graphically if you are using a graphical user interface. The third one, the console, is where you see your outputs. This is the main output window. If you are not if you don't want to enter a few steps or a few like you have to do a calculation which you don't want to unnecessarily save, you can run a quick calculation here directly by entering the command without really having to save it in your source code. And lastly, the panel which shows plots, packages, help, and various other functionalities. So these are the 4 broadly used panels that we typically make use of. You may want to organize them the way you want. There's no fixed rule. The way it is organized like this is just because I'm comfortable with it. You should feel free to use it the way you want. Okay, to prepare the analysis, the first step you need to do is to install a package rpresence. Unfortunately, and there's a very silly reason, but unfortunately, rpresence is not available on the CRAN repository. You have to download it from a repository of which is a university repository, but again, it's available for free. What we will also do is we will share with you today an email from where you can download it. But once you have downloaded it, you can simply click on install.packages rpresence, give it the address where the package is stored, and it should install it for you. The other package we will be using, or we would like you to use, is ggplots. It's just a very cool graphical plotting interface, from making simple plots to complex animations, and also making animal movement animations and a lot of other sophisticated maps. It does a lot of that work. So again, that's not necessary for presence occupancy analysis, but you might as well want to consider. So once you have installed the packages, you use the command library in the brackets rpresence to invoke the package. Now the reason, and this is quite funny, I remember Daryl mentioned the reason rpresence is not on CRAN repository is because whoever are curating the repository, they want it to be small r and then presence, or capital R and then small presence. So there's just a little bit of a hitch there, that Daryl and others who have created it, they want it to remain presence with a capital P, but the repository owners, they want it to be small p. Some really very trivial reason, but the good news is that you can still download uh, the you can still download the R presence from other repository beyond CRAN, and it's a fairly robust software. I've tried to use other tools as well, and that's just me. But I've tried to use Unmarked, and I found it a little more difficult to work. R presence, it's been very convenient to work with. So highly recommend using R presence if you are planning to use the analysis here. Lastly, now how do you input your data? We give name to each object. We create an object for the three types of data we have. We will have, in this case, we will have detection data, which is whether you saw it or not, right? So there will be a detection history. So in grid A1, observer 16, 17, 8, 9, or whoever, whether they saw or they did, whether they saw an 8 or didn't see an 8, there will be a value of 0 or 1. Now you look carefully here. The numbers are not zeros and ones, but there are some arbitrary numbers, 5, 3, 9, 7. These are the times you people took, the observers took to enter this data. In an ideal world, we would suggest you clean it up, and for anything that's not 0, you make it 1. Anything that's 0, you let it be 0. Whatever is NA stays as NA, as you can see here. But the good news is our presence is clever enough that for a single occupancy, single season or a single occupancy analysis, it automatically transforms anything that's not 0 as 1. So you, even if you forget to clean it up, it'll still work for you. But I will again recommend it to keep it clean. It's better to change it from zeros to whatever arbitrary numbers to zeros and ones and NAs. It's usually a good practice. But before that, by doing read CSV, you will be, and this is the file that we will share with you. This is simply this detection function, this detection history. And if you want to clean it, there's again a very simple tool in Excel. It used to take us a few seconds, but in R, it takes a few microseconds. Just this command, you put it there, and it will transform your entire data from 5, 3, 9, 7, 5, all of these, they'll just be transformed to zeros and ones. One of the simplest data cleaning tools or commands that can do that transformation for you in a fraction of a second. So the reason we need to do it, or we should do it, is because each of these cells represents where you saw a species there or you did not see a species there. That's all it represents. The third category is that whether you even surveyed it or not, right? So these are the roughly three, broadly speaking, three categories that should go in, which is why we've just cleaned it up from a random number, not a random number, but the amount of time you took to detect it, to a 1. Whether you saw it in 3 seconds or 8 seconds or 20 seconds, as long as you saw it, it's a detection. If you did not see it in that period of time, it's a non-detection. If you did not survey it, it's a NA. It's not applicable because you haven't surveyed this. I'm sorry, I'm just kind of going back to the same things again and again, but given the number of data sets we've come across with these few things not fixed or missed out, especially with large surveys, if you have a few errors like this, it takes weeks to fix those errors. So it's always a good practice to keep the basics of how the data is needed ultimately right from the beginning. Keep that in mind before entering the information on the computer for analysis. Now, we need to input the survey covariates. What are survey covariates? Those covariates which would potentially affect the probability of detecting a species, in this case 8. The probability of detecting 8 in a grid cell could be a function of how much time you had to survey it. It could be a function of how far you had gone from 1 to 25 surveys. Maybe you were tired, or maybe you were just getting better and better. You're getting practice there, either of the two. So these are the two survey covariates. One of them says sequence. One second. Yeah. One of them says sequence and one of them is time. They're two separate files, exactly how we had created. I've gone the long way rather than being smart enough to right from the beginning create those long tables. This somehow was easier for me. So I went this way, put the data together, made two separate files, and then brought them together. How did I bring them together? There's again a very simple means to do it. R allows us to reshape the data from a wide format where we had for each cell, for each site, for each observer listed in columns, for each site listed as row, there was one value. I'm just transforming it into a long format. These codes, again, once you use them, you'll start getting used to it. It's very straightforward. By the end of it, what it does is you will have the data in the same format which we wanted, where you will have A1 by observer 1, what were the values of time that A1 had for observation 1, and what was for observer 1, and how much time observer 2 had for the observer 1 had for how much time the person had, and how much what sequence it was in. Again, fairly straightforward. They look a little intimidating, but if you want, we can spend some time later on this, but I'll be able to explain what it does. It's just basically transforming the data from a wide format to long format, and that's why we call it reshape. And that's an inbuilt function in R. You don't need to install any packages to do this. Now to input the habitat data, which is the covariate data, which might affect the probability that 8 lives in a grid cell or not. Now, we are making an assumption, or we are making a hypothesis that the distribution of 8s was a function. Whether it was a positive function or a negative function, we don't know, but we suspect that 8 was related to habitat. So we are simply entering the CSV file, which has habitat of 8. And in this data set, you remember we had two columns. One column was habitat as a continuous variable, and the other column was habitat as a categorical variable, 0 or 1. Predominantly green, predominantly white is 0 and 1. Proportion of a grid green is anywhere between 0 and 100%. That was the continuous variable. Now, moving forward to the next one. This is an important step, and again, many times we all miss it, but it's a very crucial step to standardize your covariates. Now, it's important to standardize covariates if you are trying to compare multiple or responses of more than one covariate on your probability of occupancy or detection. Doesn't matter. It is important because you will notice that in this case, each covariate is likely to vary between different ranges. Now, in this case, altitude is varying between, in this case, let's say 500 meters to 4,500 meters. So you have a range which is from 500 to 1,000, 1,500, and so on. So the range is between in hundreds, right? And on the other hand, you might have a proportion of a particular habitat, in this case pastures, which is in percentage. Now, percentage will vary between 0 and 1 or 0 and 100. Proportion will vary between 0 and 1. Percentages will vary between 0 and 100. But look at the two. One is ranging between 0 and 100. The other one is varying between in many thousands. When you try to use them together in the same model, the because it's a mathematical model, it will be dealing with two of them at very different scales, and depending on how much accuracy at what level of decimals you're working at, you might end up having spurious relationships, or even if you have a reasonable relationship come out, you will never be able to compare the responses of your occupancy or detection as a function of these two very highly variable ranges of your covariates, and make a comparison. That will become very difficult. If you have to compare them, you have to standardize them so that they all become in a comparable range. Otherwise, it remains uninformative. How do you do that? Yeah, here in this case, let's say the height was 4,000 meters and the proportion of the sampling unit occupied, or the proportion of the sampling unit as a pasture was 45%. To make comparisons becomes difficult. So what we do is we generally use a practice to standardize. How do we do that? I think I talk in a second. But basically, what it also does is, even if you have just one variable, it's usually a good practice to standardize, because what it does is it normalizes the distribution of your data. So the left one, the graph you see on the left, is a non-standardized uh, histogram, is a histogram of non-standardized value of the survey covariate frequency, sequence. And on the right hand side, it's the same covariate standardized. You will see this one looks much more normal. There's some clustering around the mean, and then there is a tail, so it gets normalized. Now this was a very simple covariate. When you have larger data sets, then it becomes even more pronounced. It's always a good practice to try and standardize your covariates. How do you do standardization? In R, there is a very simple function, inbuilt function, which does it for you, which is simply called scale. So if you have a covariate time, just say scale time, create it, make a new name, give it a new name. Let's say in this case, standardized time. Then time will change from whatever it was ranging between 0, 10, and 20. Now it will range between minus some value and plus some value. What it does is, what scale does is, it it essentially makes the mean of your data, the entire data set, the mean becomes 0 and the standard deviation becomes 1. So that's the kind of standardization the scale function does. If you want to do it on a computer or a calculator, you can use this equation below. Standardized value is whatever is the original value of that particular cell minus mean of all values and divided by standard deviation. By doing this for any value in your data set, you will end up with a standardized value which will be uh, which will uh, which will be somewhere between -3 or 4 or whatever to +3 or 4. But ultimately, the bottom line is that if you take all these values, the mean will be 0 and the standard deviation will be 1. So it'll be like a bell-shaped data set that you will end up with. As you can see here, over here, you see this is the mean of your data and this is the standard deviation, -1 and +1. That's exactly what it does, the standardization step. So here what we have done is we've not only standardized the time covariate and the sequence covariate, which were detection or survey covariates, but we've also standardized habitat, which was a covariate potentially affecting the probability of a site being used by 8. Take note of one important point here, that we have not standardized a categorical covariate because it's anyway either 0 or 1. You don't need to, you don't need to standardize or scale your categorical covariates. Let them be the way they are because they're anyway dealt with it completely independently. Each of them is used as a single block. So once you have standardized your data, then you create what we call as a PAO file. It's funny, PAO, I think it stands for proportion of area occupied file, but you can call it whatever. Create PAO is a presence object. Your data is brought together. The site covariates, survey covariates, and the detection history. It's all brought together and converted into a single object. Here, what we are doing is, if you look carefully, we're taking the detection file, which was zeros, ones, and so on. We're taking the habitat covariates here, and then we're taking the survey covariates, which we have transformed into a long format. There are two small steps here. What they basically are doing is, presence files do not need information about which site it is, whether it's A1, A2, A3. It doesn't care about it. It just treats them in the same sequence. So as long as your unit, it assumes that your unit covariates or the site covariates are organized in the same sequence in which your detection data is, and both of these correspond, at least your detection history corresponds exactly to how your survey covariates are. So as long as your data is in the right order, it will not have any, you will not have any problems. All you need to do is you need to remove redundant uh, columns, because they're not used in the analysis. So that's the only one key step that I have done. All I've done is remove column 1 and column 2. Here I've removed column 1 of the detection history data. So once we've done this, then your file looks something like this. You will notice that there was a site here, and this site is now gone. Similarly, I think, yeah, okay, so there we go. Yeah, so this particular data goes off, and this also goes off, this also goes off. So to remove these three columns, we are using -1 from the find history, that file's here. And to remove these two columns, we are using this particular sub command here. And that's about it for now. Because PAO files does not like these additional details, it's very important that you remove them. Sometimes you might want to remove them within Excel so that you don't have to do this step in R, but it's always a good practice to let your Excel files be there, because to cross-reference and do other things, it is sometimes important. So it's a better idea to leave your Excel files fairly detailed the way you want them, and then make these modifications in these PAO objects that you have. Now, let's do one thing. Now we will run our first null model. What is a null model? A null model is a model which assumes that probability of occupancy and probability of detection, they're both constant. Or in other words, think of them as they're totally random. There's no pattern. They're absolutely totally random, and we can give them a mean value around which they might be distributed normally. So that's what it assumes. A null model is a model which assumes constant psi and constant probability of detection. Now, there are a few things you might look here where this SO. Now, there are many. The SO here stands for a single occupancy. There are at least 8 different types of uh, occupancy models you can run. You can run a model with instead of SO, you can go to the notation. It could be, I think, I don't remember any of them right now, but it could be, I think, 2SO, which means uh, um, 2SPSO, which is two species, single occupancy, and then dynamic occupancy, and so on. I think 2DO is for dynamic occupancy. Again, I'll show you in a few minutes how to find those details, but they're fairly simple. I thought I had copied them, but I seem to have forgotten to copy them here. But bottom line being, you can choose what kind of an analysis you're doing, and it will allow you to be able to run that. Then, okay. The only thing you might need to remember, by the way, is in this workshop, we are only going to deal with single occupancy models. If, however, you are interested to deal with other types of dynamic occupancy or multiple season models, or models with false presence, or a model where you're looking at correlated detections, we might need to plan a separate workshop. But please let us know if those are of your interest. Then I'm sure Justine and Raki will be able to help us.
Yeah, we can always do extra sessions.
Yes.
Forever and ever, Kostu.
All right. Okay, here we go. Now, once you have run the model by just simply punching in this command, what you can do is you can see what it looks like. And the steps very simple. Just say summary and name of the model that you run. What you will look here is some familiar numbers. This one is showing AIC. We'll come back to what AIC means and why is it important. And then it shows the log likelihood as 143. There is a bit of a warning, and this warning is primarily because it's a very small data set. We just had 25 sites repeated about 8 times. So it's not a big data set. It's a very relatively small data set. So it does sometimes complains when it does not reach convergence beyond 7 digits. 7 digits is anyway a lot, right? It's fairly uh, uh, it's fairly good, but it's kind of spoiled for options or for precision, and it really is seeking greater convergence. But for now, let's assume that it's doing a fairly good job. The other thing you will now do is the model has run. These are AIC values. What does the estimate mean? So when we run the estimate, when we want to know what is the psi or what is the probability of sites being occupied, we use the function fitted. And then here we mention psi. So we are estimating the fitted parameter and we are looking for psi. So what is the psi? The only reason I put unique here is because occupancy estimators, they estimate psi for each site. So if I don't use unique here, I'll get a list of 25 sites. Actually, we've used 30. It'll give me a list of those 30 sites where 5 of them were complete NAs. So it'll give me a list of those 30 sites and it will give me a value of psi for each of them. But since it's a null model, this value will be repeated in each of them. So if I don't use unique, I'll have this line repeated 30 times, and that's the value I'll get. What it's saying is that my probability of occupancy is 0.38. It could be almost 0.2, or it could be as high as 0.56. How do you reduce this? The way to reduce the error is, in this case, is to increase the number of sampling units. And how to do that? We expand wider, we collect more data, and that's how we get it. If you look here, again, the same equation. The only difference here is that I have used, instead of P, I have psi. Now I use P, and when I use this, I come up with this estimate, and what it gives me is an estimate of probability of detection. What it's saying is that each observer, which means each of you, had 50% chance of detecting 8 in a sampling unit. That's what it is indicating. You had half. So in other words, if there were 10 sampling units that had 8s in them, you were likely to have detected them in 5 of them. That's what probability of detection here means. Each observer's probability of detecting an 8 in a sampling unit is what's being reported here. Does that make sense? So with that, then we go to the next step. Okay, so this is simply how we visualize, or how we come up with the very basic standard null model telling us what is the overall probability of my sampling units being occupied by 8s. Here, in other words, you can also say that if there were 100 such sampling units, 36 of them would have been occupied. Well, technically speaking, because the confidence interval is wide, I can say that if I had 100 sites, anywhere between 20 and 56 sites would have been occupied by the species of my interest, in this case 8. Now we go to step 2, where we make it a little more complex, and you have to be a little careful on this step, because this is where we will be incorporating detection covariates. What we're going to do is, now you remember we were hypothesizing that probability of detection is a function of sequence, right? From 0 to 25, as we went further in sequence, we were getting more and more we were becoming experts at detecting 8. Or conversely, as we were going from 1 to 25, we were getting exhausted and doing a lot of missing out a lot of them. We don't know which side is true, but we will test it. And to test it, we simply create a model which says psi is constant. Oops. Psi is constant, but P is a function of sequence. Similarly, we create another model where we say psi is constant, but P is a function of time. Remember, these are all STDs, because these STD means standardized, which is scaled. So these are not raw data which range between 0 and 25 or 0, 10, 20. These are standardized. So now they are between minus something and plus something, so that their means are always 0. The third one, where I'm looking at more complex relationship, I'm expecting that the detection was a function of not just time, but also sequence. So maybe one increased, the other decreased. Maybe both of them were helping me improve. We don't know what direction it takes, but I'm just thinking maybe it's an effect of both. And you can add more covariates, just that each covariate you add has a cost associated with it. And what is that cost associated? We're just going to look at it now. Now, this is a very important element that you need to understand, which essentially helps us balance between model complexity versus model replicability. Let me show you this one. Now, consider this model on the left hand side. It's the same data that you might recollect we collected, we were doing the other day, where as distance from the water increased, there were fewer and fewer animals counted in those little blocks, right? And then we converted it into a exponential function and whatever. But right now, just let's keep it a simple thing: a linear model, straight line equation, or a polynomial equation. Now, if I show you these two graphs, definitely what looks like is yeah, what certainly looks like is this one is really making, it's matching the data fairly much better. And how do we confirm that? Simply r square value of this one is 0.82, which is fairly high, fairly close to 1. When a distribution of points matches an equation, or a regression completely, that becomes 1. Here it's trying to get as close as possible to 1. Now it's doing well. If I draw a straight line, my r square value is slightly less, 0.72. But I might actually go ahead and prefer this one over this one. And the reason for that is, for this particular data set, my model is doing fine, but is my model general enough to make predictions beyond what my actual data points are? What if I get 5 more points, and those 5 points are somewhere here, like this? So even though they are very close to the points, they're still, now what will start happening is, oops, sorry. Yeah. Now what you start seeing happen is your model starts failing the moment your data exceed, or the moment you go beyond what your actual data is. Now this is the cost of model complexity. The more, and look at this, you have 1, 2, 3, 4, 5, 6, 7, right? It's a 7 order, it's a 6 order polynomial equation. It's fitting my data better, but it is going to do a very poor job of predicting anything that's not already listed in my data. There could be a much more detailed model further, which could be something like this. You know, fair enough, fits perfectly, but does this line have the ability to predict a new point's location if I have another distance? Let's say I have another distance here. Can this model predict what will happen at this point? It will have a problem. And that's where we lose some precision, we lose some fit, we lose uh, some ability of fitting the data with the model at the cost of generalizing and being able to make broader predictions. In other words, we want the models to be as simple as possible, but yet informative enough that they can explain a certain number of patterns. And that kind of a balancing act is not possible when you're just, I mean, in other words, if you have 20 parameters, and a lot of models use those, a lot of modelers use, let's say, 20 different parameters, you plug them in, they'll become very nicely, they'll fit very well. Your RUC, a lot of people do this, RUC, area under RUC curve, it'll be very high. But is that model able to predict anything beyond what you are entering into the data? And that's where it starts failing. And that's where the problem comes with highly or overfitted, overparameterized models, that they start overfitting your data. And when there is a problem with overfitting, then you end up with a challenge of not being able to do a good job of predicting. And how do we deal with that? The best way to deal with or to find a balance between the number of parameters and the fit is using AIC. We call it Akaike information criteria. There are various evolutions to it, but the standard AIC is as good as anything else. In fact, it does a fairly good job of balancing the number of parameters added versus the fit. So if the fit hasn't improved enough for an addition of another parameter, you will end up with a higher AIC value, saying that it wasn't worth adding that additional parameter because your likelihood hasn't improved significantly that much. And that's how it does a very good job of balancing it. How do you do it with your occupancy data set? It's again a very simple thing. All the models that you have run so far. Now, you remember we ran these 3-4 models here. We ran, first model was find 8 sequence, find 8 time, and then find 8 time sequence. We go back to the same 3 models, and when we look at the output, we list them all together. Sequence, time sequence, and also null. You remember the first model we ran was the null model, where we are assuming it all to be constant. We're assuming that there is no effect of sequence or time on detection probability. You do this step, you list them together, then you create another, this is another R presence specific function. You create an AIC table based on this list of all these models that have been run, and then you summarize it. It will give you a table, and the table would look something like this. The table will look something like this. It's one of the most informative outputs you have to begin with. What it's doing is, you look carefully, the negative likelihood is an estimate of how well a model is fitting the data, and this is the number of parameters. Now look at this carefully. The lower the negative likelihood value, the better is the fit. So this model is fitting better than this model. This model has 142 likelihood, and this model has 140 likelihood. It's fitting better, but it is still listed secondary because there is one additional parameter that has added here. And the cost of that additional parameter is not worth the gain in likelihood that you would have wanted, which is why the AIC value is is uh, is uh, is smaller in case of the first model, which is the null model. So, in other words, this very simple exercise has tested three hypotheses: whether detection probability is a function of time, whether detection probability is a function of sequence, or whether detection probability is a function of sequence or time put together. And it's testing them versus the hypothesis that detection probability is constant. And here, based on this AIC table, it's indicating that yes, you do improve your fit, but the improvement in fit is not worth the cost of adding another parameter. It doesn't really add much to your data. Your detection probability might get slightly better, or your estimates might get slightly better, fit slightly better if you add the time model, but not that much. So it's not making that much of an impact. And that does seem to make sense. Apparently, the way you guys were detecting eights, there were a lot of 10-second displays where you got a lot of hits correctly, and the number of hits that you got in 10 seconds wasn't significantly different than what you got with 20 seconds. So that's what it's saying, that yes, maybe there is an improvement, but the improvement is not significant. So it doesn't matter. You would have assumed it would have improved it, but not in this small study. It hasn't made an impact, and that's what it's primarily suggesting us. The next point we look at here is, now that we have incorporated survey covariates, now we include site covariates. What are site covariates? Site covariates are those which affect the very presence of 8 being in a particular sampling unit or not. And to do that, same thing, the model is being done the same way. The only difference here is, here we are formulating it like this: psi is a function of habitat, psi is a function of binary habitat, which is zeros or one, or this one, a slightly more complex one, and this is primarily for you, Chloe, when you mention, what if the relationship is not linear? What if the relationship with habitat type is non-linear, that 8 likes it, or 8 loves gray habitat? It seems to like a little bit of green, but when it's too green, it just doesn't like it also, or the other way around. What if 8 loves a little bit of gray, completely hates moderately green areas, but just loves very green areas? So these variations, these non-linear relationships, you can test. But again, remember, every new parameter added is at the cost of the generality of your model, of the predictability of your non-model data, which is why the AIC penalizes the estimator for each new parameter added. And in this case, it's a simple squared equation. I'll explain it, I think, in a couple of seconds. Yes. And what you end up with here is, when we run these three models, what we come up with is, again, you compare your models, and now you remember these were already listed. These were my previously run models. I'm now adding these three new models to it: the habitat model, the binary habitat model, and the habitat as a occupancy of 8 as a quadratic function of habitat model. Same steps. I do this, I create an AIC table, and when I run the summary here, let's see what I get as outputs. Yeah. Now, what you're seeing here is at least for this little data set, it's a nearly complete analysis, minus, of course, the covariate that we don't have, which is that of the screen size. And if it comes, maybe it will improve our estimates further. But for now, what it is suggesting is that those sampling units which had, we don't know whether it's positive relationship or negative relationship. What it's saying is that the probability of 8s being in a habitat which is which is green, was different than the probability of those sampling units being occupied by 8 that were gray. So the probability of use of habitat green versus habitat gray was significantly different. That's what this model is suggesting. And you will see that it has among the best fits, as well as yeah, the number of parameters is 3. So you will see between these two, the fit has gotten better and no additional parameter added. So it just said, you're actually doing better with the model which uses binary habitat. And that's the estimator which we are going now see and explore. What does it say? So to come up with what the model is showing, there's another very easy way. You can, once you have an AIC table, just say this is the AIC table, click on model and give the address as the first one, and that's the top model. You take the top model, and this is a function that you use called coefficient. When you use the function coefficient, it tells us the value of psi. In this case, it's giving me a coefficient of psi which is 0.2 for habitat and minus 1.7 for this is the intercept. What does it mean? You remember the straight line equation, then we converted it into a logistic regression equation. This is exactly what it means. So in other words, let me just show you the next slide, might be clearer. If you have the value of habitat for each sampling unit, what our occupancy estimator has done is it has given us a value of beta 0 and beta habitat, which here are these two values. You look at it here. This is my beta 0 and this is my beta habitat. Now, if I use these values in the estimator, it's just going, you can use this equation, and for each site you will give a value of psi. That's all this equation is doing. It has given us a value for the coefficients beta 0 and beta habitat. You multiply it with the habitat's value. In our case, it's ranging between minus 2 or 3 to plus 2 or 3 because we have standardized it. And you enter each of those values, and for each of those values you will get an overall value of psi, which will be the probability that that particular sampling unit is occupied by an 8 or not. In our case, what it's indicating is that your psi, or the probability that your sampling unit is occupied is, I don't know how, well, oh yeah, now I know. It's saying that it's higher for those units where the habitat value is 1, and it's lower where the habitat value is 0. So what it's clearly saying is that it prefers those habitats which are predominantly green than those which are predominantly gray. And that's what you get from these values, because if I put minus 1.7 plus 2.0 multiplied by habitat 1, then whatever value I'll get, this will be the situation for psi which habitat is equal to 1, and psi with habitat is equal to 0 will be minus 1.7 plus 0 upon minus 1.7 plus 0, all of this on exponential scale, same equation. So in other words, if we use this equation based on the simple signs of these coefficients, we can say which of the covariates has a positive relationship, which of the covariates has a negative relationship. And that's how we define the relationship. Just to see it more graphically, I'll show you in the next slide. Over here, top model. The first model in our case is habitat as a categorical coefficient. Look at it here. For habitat category 0, my probability of occupancy is less than 0.2 or 0.17, I think. And for habitat category 1, it's 0.57. Meaning, in my entire study area, those sampling units that had those sampling units which had which were predominantly green are more likely to be occupied by 8s than those sampling units which were not green. And that's how we come up with this one equation. There can be another. Let me look at the second best model in this case, which was the model which said occupancy as a function of
Kustub, your sound has gone funny.
occupied, and that's what this indicates.
Ah, you froze for a second. You're back. You're back.
Okay, sorry. Okay, if I freeze again, Justine, just mention, because then I'll change my internet.
Okay, I'll let you know.
Thank you.
And
Okay.
I think we're going over a little bit, but please stay with us, because I think these will be really important notes for when you actually analyze. I know maybe now you're thinking, oh my God, but you can go through it, the recordings, when you analyze, and it will be a really nice reference.
Sure. And lastly, if I may show you, thanks, Justine. Lastly, and now it's all visualization, so don't worry. This is the quadratic equation. It didn't perform very well. If you look back, it was the third best model. You see, the third best model, the AIC weight was only 10, almost 11%, which means that it's not very, there's only 11% of the variation in my data within the sets that we've compared that justify the possibility of my relationship between habitat and probability of presence of 8 as a quadratic function. And in this case, given the sign, the way we are getting it is like this. So what it's kind of saying that if this particular model was the top model, then as the habitat value increases, the probability of 8 using them reduces. So 8 does not like intermediate green. It either likes less green or it likes very green. Actually, it loves very green because that's where it's the highest probability, but it doesn't seem to like those which are partially green. So the same situation would have been reversed in a certain case. Let's say snow leopards. Snow leopards, they don't like very low altitudes. They don't live on very high altitudes because there's nothing to eat. Low altitudes, it's all vegetation, trees and all. They don't manage to hunt very well. They live somewhere in between. So in case of snow leopards, in an ideal scenario, you might have received a relationship such as this one. Which one is true? We let our data speak rather than us. Now, based on the outputs that we have got from our models, this is what it looks like. And if you look at and compare this with what the real scenario is, you will notice that it's fairly compliant. It's doing a fairly reasonably good job of giving us an estimator which is as close as possible to reality. Yes, it has failed to give a high probability of occupancy in this particular unit. It has falsely predicted snow leopard space use in this one. It has sort of kind of gotten confused about these two, but these are outliers. With large data set, this can possibly result in a fairly good understanding of what's happening. And this is where we use, so over here, if you see these circles denote the errors. Bigger circle means more error, smaller circle means less error. But uh, uh, basically, this is what it indicates. So what it's saying is, in this case, we have just used the second best model, but we are saying that as the habitat value increases, the probability of snow leopards using it increases, and it reduces with these that have less and less of white habitat. So that's how we start from the step of organizing your data to looking at how it should be it should be set up in a way that there are biologically and ecologically meaningful relationships that you're exploring, and then you come up with a modeling exercise which goes through certain number of steps as we've just discussed, and then you come up with the output. Now what I'm showing right now is not the top model, it's the second best model. uh, just for visualization sake, because there was a bit of a variation here, I've just shown it here, but the top model is very close to what this one looks like. And that's with that, I think we can stop now. Sorry, as usual, 7 minutes over, actually many more minutes over, but
It's okay. And we can actually go maybe into questions. We had also
yes.
planned to look at goodness of fit, but we can save that for next session and do questions related to analysis, I think. Thanks, Kustub. I think it's really helpful to have, you know, that it's almost like those annotated YouTube videos that share how to do R and analysis. So I see a lot of value in your presentation. So thank you for taking the time to do that. We have a question from Ursa.
Oh yes.
Let me see.
um, yeah, you're absolutely right, Ursa. The only reason why we have them separately here is because our top model did not want any detection covariates. In real life, you if you if you end up with some, you might as well bring in more detection covariates once you have zeroed in. So it's almost like a bit of a going back and forth exercise. But yes, some, you know, if we had a covariate, and I'll strongly urge, please bring in your screen size. Who knows, there could be a factor there. But if there was a covariate which was affecting detection, then it's definitely affecting our occupancy as well. So that the models, everything goes in. So this particular example was such that the detection covariates did not do much. They were not really worthy of an additional parameter. But if they were, we would have added them. And that's exactly what we typically do. So we try to find those factors or those covariates which are affecting detection and zero in on those which are making sense, and then start using them to estimate the site covariates, and then ultimately we test. We come up with those models which are the best possible combination of site covariates and detection and survey covariates.
So can I add, Kusub? You can do it in a 2-level approach. Some publications suggest that. So you first test detection covariates, not the same as the site covariates, your detection covariates you hypothesize, and see which one is the top, and then take that top one to test your site covariates. This is helpful with low sample size data sets when you can, and it's difficult to add too many covariates. But that's an approach often used in publications. And it's not the only approach, though.
Yeah. Yeah. So typically, Ursa, just to reconfirm, as Justine said, once you have a good selection of survey covariates, you might then start using those survey covariates the way they are and start putting site covariates. And then once your data, you get even better and better, I mean, your AIC reduces further, then you come up at those models which will have the most appropriate site covariate and the most appropriate survey covariate. So that's how you go. Maybe this wasn't a very good example to showcase that, and we will be sharing with you another exercise where you will be able to see that a model or a modeling process where you end up with one or two site covariates and one or two survey covariates which jointly provide the best estimator. Right, Justine? That makes sense? Yeah. Okay. Any more questions?
And we'll talk next time. I mean, you do AIC to compare models, but it's also important to look at your global model and see actually how it fits your observed data in itself, because the AIC is really comparing models against each other. It doesn't really tell you if all your models are crap. Sorry, because
Yes.
there's one lousier than the
Absolutely.
other. That's
Yeah,
all it's really
absolutely.
saying, right? So you need to
Yeah.
also know your model in the first place, a good model and not over parameterized.
Yeah. Absolutely, Justin. I mean, essentially AIC is only a relative term, right? If you run 5 models, it's just saying out of these 5 models, this model is the best. That's it. Whether the best model is, as you said, crap model, we don't know. And to do that, there is a separate test which we do, which is called a goodness of fit, and it's a fairly simple, straightforward thing to do, but yeah, it
If no one
helps.
has questions, should we just do that really quickly? It's just
Might as well.
5 minutes.
If yeah, I mean, we gave a
If
five
you
minute
guys
break. Come on.
okay?
One question.
Oh yes.
Yeah, Chloe, that's the exact question we wanted to cover today.
Yeah.
Can we
Justine's
do
gonna do it
it
now.
over 5 minutes? Is that
Yes, please.
okay?
Yes, please.
And
Go ahead.
other people can watch the recordings. Okay. So we were just going to show quickly, just talk about goodness of fit. And as we just explained, AIC really looks at trade-offs between models, and whether, and it doesn't really assess whether your model is lousy in the first place or all of your models are lousy. So in other words, how do you know if your model really predicts your observed data? Because in that case, that's what we're trying to do, right? As Kustub explained with the curves, how well those curves really predict the actual data. So you can do a goodness of fit test. And that's why we do it, is to assess if our models predicts well our observed data. And McKenzie and Bailey 2004 is a paper, a good reference for occupancy models, because they suggest an approach of comparing observed and expected detection histories. And then you can just use a simple Pearson chi-square to assess the fit. And this is in single season occupancy models. There are other approaches maybe to consider for other models. And this can be done in R, and we'll share that script as well. And we did it with our sample data, and we'll explain the results from that. But what does that mean? So when our model parameters, we predict a detection history, as we just explained. And this, for example, is our model prediction for our area. And we predict also a detection history, 1, 1s, or 0s. It's not only just the occupancy results. And we can compare that with the detection history that we actually observed, so our field observations. So we can then, it's comparing the observed and expected and seeing if they're similar. And you can do that with a simple statistical test like a chi-squared test. And the two may not match. And then they don't match because they've violated some assumption that we talked about at the beginning of class, or maybe we use covariates that were not actually suitable. So it's important to assess goodness of fit, and it's always important to do this. And basically then, so this is the equation that's actually used in the chi-squared test that is suggested, and it's basically comparing observed with expected data set. And then you use a parametric bootstrap to stimulate more data histories and estimate over dispersion. And then you get an over dispersion parameter called C hat. So basically, if your C hat is 1 or less than 1, then it indicates that your model is an okay fit. But if your over dispersion model of C hat is greater than 1, then this indicates that your model is potentially over dispersed, and then the recommendation is to use that C hat because it affects your standard error. So in the end, what happens is if your model doesn't fit, then the precision of the parameter estimates are normally underestimated, is normally what is happening, and the standard areas look better than they really are. So it's suggested to use the C hat to adjust these standard errors. And we tried to do this with the global model. Yeah, so I mean, that's all I included today, to share a little bit about goodness of fit, because I didn't want to get into bootstrapping and see how, but Kustu, maybe you can add a little bit more.
Yeah, thanks, Justine. I think that's really very simple and informative. Bottom line being, take the model which has the most number of parameters, run it using this very simple code to do bootstrapping and to come up with a C hat value. Check if that C hat value is more than 1 or less than 1. The closer to 1, the better it is. If it is more than 1, it's a bad fit. If it's way less than 1, is it 1 or 2? I forgot. Just see, is it 1 or 2? I think there'll be notation available there. But if it is too low, then it's overfitting, and that's basically informative enough for us to be able to make a statement that yes, um, it's a model which is good, and now henceforth the AIC value becomes more important. Henceforth, you use AIC value to define how relatively how good are the models than the other models, and that's typically what we need to look at, which is what I think the goodness of fit does. So yeah, thanks so much, Justine. That's so helpful.
But yeah, there is a call for more statistical approaches, more advanced approaches on goodness of fit for occupancy. I remember Daryl highlighted that it's still needs to be looked at, and more tests need to be developed, because some of the more complicated tests, it gets complicated occupancy models, it gets more difficult to assess model fit. But yeah, it's with the global level. I hope that provides a little bit of information. And Kustub, we tested it for our data set, and we actually, for the top model, did you test it with the global model?
I did actually with the global model, and it gets us a C hat of 0.7 something, which is not bad. I mean, with such a small data set, such a small study area, limited exercise, I know everyone was getting tired with counting eights, but yeah, it's not bad. It's not bad, and it's doing a fairly good job. So good.
Great. What exactly is the global model? Sorry, yes, great question, Ursa. Feel free to ask. Sorry if we go ahead of ourselves. Global model is with the most parameters in your model, whether it's site and detection parameters. It's the one with the most.
In other words, typically what happens, see, our case was a slightly special one. Let me show you here. In typically we haven't even listed the global model here. Can you see the screen, right, Justine?
Yes, I can.
Okay. Yeah, so typically a global model would have used hold on. There. It would have used all these variables and both of these, and that would have been my global model. We would have expected the global model to have the minimum negative likelihood value. So the model which has the least likelihood value, which means the highest fit, is what we typically use. You can use that, or in this case, what we used was the model which had the minimum likelihood, and which was this one. And we thought that if this is fitting well, thankfully, we also have a model which is also the top model, and that's because it has the minimum negative likelihood as well. So it's the best fitting, the least number of parameters. What else can you want? So for us, it was a simpler case than otherwise. But as Justine is saying, global model is the model which uses all the parameters that you are working on. Just put everything together and then see how is it performing. But when you put everything together, make sure you don't use covariates which are correlated. Like we cannot run psi as a function of habitat plus habitat 0, 1. That would be wrong because they're the same thing. We're just calling them in different terms. They're basically very highly correlated with each other. Doing that will provide spurious relationship. So we avoid doing that. in everything else, this one is fine because we're just doing a polynomial equation of the same variable. That's not a problem. But doing this is not the right thing to do. Thank you. Thanks, Justine. That was useful.
Thanks, Kustub. I hope we didn't go over it too fast. I realized after I went really fast. Yeah, if you have more questions, feel free to send us over email or just get in touch. And we'll have our final session next week, and Ian will come and join us and talk about some other approach. And we're going to talk about applied occupancy. So do join us for the last session next week.
Cool.
Thanks, everyone.
Great.
Thanks,
Thank you
for
Justine.
doing all of that sharing with R.
Not at all. It's fun.
Yeah.
Especially
Really?
to see our own data collected on a new experiment in the workshop. I think that was more fun for me than anything else. So it was good. And we'll be sharing the codes as well as the data that you have collected.
It's good we tested our hypothesis. You don't learn to get better at spotting eights, basically.
Yep. It's a mixed response, which is somewhere between exhaustion and learning. So it remains constant. It doesn't get better overall. It's kind of a mixed response there, probably. That's why it neither gets better nor gets worse.